Do you have any stapler? I did not bring my stapler. I'll run upstairs and grab it. Oh. Oh. Okay, folks, I should have everybody's lab. If you haven't turned in your lab, please bring it up. I have a stapler. It doesn't matter. I'm sorry. Okay. So before I get started into today's material, do you have questions?
So if we do the practice problem or optional homework, and we feel pretty good about all the questions in that, I think that's good.
If you do the optional homework, you should be prepared for the exam. I would say in response to that question, if you do the optional homework and you come across something that you're still uncomfortable with after doing the optional homework, that will give you an idea of what you might want to ask me questions about, or ask if I have additional problems for it. So that will be the next target. But yes, the optional homework should be a pretty good study guide. I think there was one series of questions that I don't think appears on the optional homework. And this is related to the quantitative Villa solution form. And there is a table where I gave you if the solvent interaction is stronger than the solute and solvent interaction, then a solution will form. If the solvent interaction is equal to the solute plus solvent interaction, then a solution will form. It's only if the solvent interaction is weaker than the solute plus solvent interaction that a solution may or may not form. I think that's the only, and again, I gave it to you as a table in class, but I think that's the only tidbit of information that doesn't appear on one of the optional homeworks. Everything else appears similar to what it does on an optional homework. Other questions? Okay, if not, we are going to get back into our topic associated with rates of reactions. On Monday, I gave you a generic reaction of A plus A plus B goes to form C plus D. And I wrote a generic rate law. Rate is equal to K times
the concentration of A raised to some power times the concentration of B raised to some power. This, folks, is a generic rate law, and the entire focus on this is that it always has a similar form. It is always the rate is equal to the rate constant times the concentration of the reactants raised to a power. That power is called their order. The order can be 0, 1, 2, 3. It can be a half. It can be a -1, -2. In other words, there isn't a specific numerical digit or type of digit that the order has to be. The order tells you how many of that particular molecule must react in order for the reaction to occur. And it is that molecule or set of molecules that is responsible for the speed at which the reaction occurs. Now, how do you determine the order? Because at the end of class on Monday, I gave you some reactions, and I gave you the rate law for those reactions. And what we discovered is that the rate law, the order for the reactants, is not necessarily related to the coefficients. For that matter, the order is, the rate law does not necessarily contain all reactants in it. So how do you determine it? And that is where experimentation comes into play. And we have two types of experiments that we perform. One is the method of initial rates. And the second is the integrated rate law. These two methods will allow us to determine the order for our reactants. And once we know the order for our reactants, then we can write the official rate law. Then we can determine the overall order and know how many of each molecule are reacting to form the products. So we are going to do the method of initial rates today. And then on Monday, we will do integrated rate laws. So let's look at the method of initial rates. Basically, the method of initial rates is a series of experiments where the concentration of a single reactant is altered while holding the other reactant constant. The speed or the rate of the reaction is determined under these circumstances. Let me illustrate. So I have the reaction 2NO2 gas plus F2 gas goes to form 2NO2F gas. I perform a series of experiments. So my experiment 1, I am going to use 0.0482 molar NO2 and 0.0318 molar F2. Under that particular set of circumstances, the rate of the reaction in molar per second is 1.90 times 10 to the minus 3 molar per second. It's called an initial rate because literally, folks, we have a beaker of one of these, of the NO2, we have a beaker of F2. We dump them together and we determine how fast that reaction occurs. Experiment 2, we're going to alter the NO2. And we're going to use 0.0120 molar while holding the F2 constant. Under those circumstances, the rate is 4.69 times 10 to the minus 4. So literally I have 0.120 molar NO2. I have 0.0318 molar F2. I dump them together and I determine the rate. That's why it's called an initial rate, is what happens when they're first combined. Experiment 3, I have 0.0482 molar NO2, 0.127 molar F2, and this has a rate of reaction of 7.57 times 10 to the minus 3. From these 3 experiments, we can determine the order of each reactant, and we can write the rate law for this reaction. Now, to start, we're going to work with experiment 1 and experiment 3. What do you notice about experiment 1 and experiment 3? The molarity of NO2 is being held constant. That's important because when we write our generic rate law, we can write rate 3 is equal to the rate constant times NO2 for experiment 3 raised to its power times F2 for experiment 3 raised to its power and we can divide that rate law by the rate law for experiment 1. Rate law for experiment 1 is equal to the rate constant times NO2 for experiment 1 raised to its power times the concentration of F2 for experiment 1 raised to its power. Now, the term rate constant indicates that K is going to be the same for the entire experiment. And we just made sure that our NO2 concentration is the same for the entire experiment. So by putting these two together, basically holding one of the NO2 constant, our calculation, come on, becomes rate 3 over rate 1 is equal to the concentration of F2 over the concentration for experiment 3 over the concentration of F2 for experiment 1, all raised to its order. So 7.57 times 10 to the minus 3 divided by 1.90 times 10 to the minus 3 is equal to F2, which was 0.127 for experiment 3, divided by F2 for experiment 1 of 0.0318 raised to its power. This left-hand side basically is equal to 4. It's actually equal to 3.98. When it is that close to a whole number, go ahead and round to the whole number. Only if it is a decent, if it's not close to a whole number, do we hold it as is. But if it's close to a whole number, go ahead and round it. 0.127 divided by 0.0318 is also equal to 4 to the A. So our A, which is the order for the F2, is 1. Now, we need to know NO2. To know NO2, you hold F2 constant. So for NO2, we're going to use experiment 1 and experiment 2 because F2 is being held constant for experiment 1 and experiment 2. So our equation again, in this case, is rate, and it really doesn't matter who's in the numerator and who's in the denominator because you can work it either way. So rate, we can do rate 2 over rate 1 is equal to K times the NO2 for experiment 2 raised to its power times the F2 for experiment 2 raised to its power all over the rate constant for NO2 for experiment 1 raised to its power times F2 for experiment 1 raised to its power. Now, once again, rate constant, then it's in the name, it's a constant, so the K's will cancel. And in this case, if you look at the concentration of F2, we held it constant at 0.0318. So those will cancel. So this equation can be simplified to rate 2 divided by rate 1 is equal to our NO2 for experiment 2 divided by NO2 for experiment 1 raised to its coefficient or raised to its power. Rate 2 was 4.69 times 10 to the minus 4. Rate 1 was 1.90 times 10 to the minus 3. For experiment 2, our NO2 was 0.120, and our for experiment 2, for experiment 1, our NO2 was 0.0482, and that's raised to the power. So you get 0.247 is equal to 2.489 or 2.5 basically raised to some power. Yes. You're right, sorry. Never mind, that comes down to 0.249 raised to the X. Thank you. So X here comes out to be equal to 1. So our order for NO2 is equal to 1. Now that we know the order, we can write our rate law. The rate law for this reaction is equal to the rate constant times NO2 raised to the power of 1, which most of the time we don't show because if it's not shown, it's equal to 1, times F2 raised to the power of 1. So this is the rate law. The overall order is 1 + 1, or in other words, it's equal to 2. What this means, if you look back at the original reaction, the original reaction said 2 NO2 plus F2. That's stoichiometry. But the fact of the matter is, the speed of the reaction is based only on one of the NO2s reacting with one F2. When you think about reactions, we have been for all of College Chem 1 going reactants go to form products. And it's easy in our mind to think, okay, those reactants are going to combine in one step to get to those products. But that's not necessarily what happens. A reaction can occur in multiple steps. In this particular case, the NO2 reacts with an F2 to form one NO2F. Then that extra F reacts with the other NO2 to make the second NO2F. It occurs in a two-step process, not in a single step. Method of initial rates allows us to predict the rate law, and it allows us to determine the order.
Can you explain again, how do we know like what order they react? Is that what like whatever you said, like first they react to NO2 with the F2 and then the extra F2 reacts to NO2. How do you know that like that's the way they respond?
Okay, so the question is, how do I know the order of the reaction? How did I know that one NO2 reacts with an F2, making an NO2F, and then that extra fluorine that's left over winds up reacting with the other NO2? The hard and simple truth is I really don't know. What happens is we can determine the rate law for certain. The rate law can be determined for absolute certain. What we then as chemists do is we come up with a series of steps that can explain the rate law that we observe. But because we cannot get down to that microscopic level to see one NO2 reacting with an F2, we can't ever guarantee that's what's happening. That step is the first step. What we can do is we can come up with a reaction mechanism, which we'll talk about later, that explains the experimental data. So it's a hard and simple truth that we don't know definitively what's happening, but we can, through experience, start to predict what's happening. But it has to match experimental data. If it doesn't match experimental data, then it's not related.
So like if problems like this were given these numbers or like this, I'm sure there's so much time to obviously experiment.
So for a problem in class, yes, you will be given the data. And you'll have to use the data to predict the rate law. In lab, we're actually going to do a series of experiments. And one of the series of experiments, we're going to use the method of initial rates to determine one of the orders. And then we're going to have to use integrated rate law to determine the other order.
Whenever you have the 1247 to the 2449, how do you get to the 1
Okay, so let me do a little bit of algebra on this so that, because it's not always going to come out pretty. This one came out fairly straightforward, but it's not always going to come out pretty. So how can you get to the exponent algebraically? The first thing you're going to do is you're going to take the log of both sides. So the log of (0.247). Now, when you take the log of the right-hand side, that exponent comes out in front and becomes the log of 0.249. Then you would divide both sides through by the log of 0.249. Ugh, hate when it does that. And you would get 1 is equal to X. I think that's what you were asking me. Other questions? Let's look at, let me give you an one to work on. Okay, so we're going to do the reaction of 2H2 gas reacts with 2NO gas to form 2H2O gas plus N2 gas. Experiment, we're going to do 4 experiments. In experiment 1, the H2 is 0.10 and the NO is 0.60, and that has a rate in molar per second of 1.8 times 10 to the minus 3. In experiment 2, the hydrogen is going to be 0.20, the nitrogen monoxide is going to be 0.60, and that's going to have a rate of 3.6 times 10 to the minus 3. In experiment 3, the hydrogen is going to be 0.60 and the nitrogen monoxide 0.10, and that's going to have a rate of 3.0 times 10 to the minus 4. And then finally, for experiment 4, the hydrogen is going to be 0.60, the nitrogen monoxide 0.20, and that has a rate of 1.2 times 10 to the minus 3. And folks, by the way, if you use highlighters to help you in class, you can bring highlighters to tests. Experiment, just so you know, experiment 1 and experiment 2 is what I would have chosen to determine the hydrogen. Go back. Order. Whereas experiment 3 and experiment 4 is the one I would have chosen to determine the NO order. And I'm gonna let you work on it. Don't forget your calculator on Fridays. Cell phones aren't allowed. I'm gonna figure it out while y'all are figuring it out. Yeah, it's not gonna matter because it comes, you can always, if you get a fraction, you just take the log of each side, so it'll all work out one way or another. It depends on.
Basically, when you this size is yeah, to get rid of that, you're going to divide both sides by the log. So much. It's just unnecessary.
I'm sure it's really building one death, but we have- Like the upper side of the wall.
You can do it either way. Thinking is this right hand side was raised to the power of X, so when you do it, the X comes out, so it's always gonna be divided by whatever. Is this making it better? Oh, yeah.
Doesn't matter, like, which grade you're from.
Like, I'll just get.
No, you just have to write it out. I write it out.
Your chicken is. The chicken has the.
No, I Shut up.
It's not like, it's like objective. Okay, so now I
So it's just me.
solid 15 seconds, so nobody else is looking at it except for now, but it's.
Oh, wait. Two, three, it looks way better.
It's like a signal to yourself.
That's not like that.
Well, these would be to even use your calendar, because that's signaling to yourself that this is. Oh.
Okay. So for the hydrogen, I used experiment 2 and experiment 1 because the nitrogen monoxide was held constant. Therefore, when I calculated it out, the order for hydrogen came out as 1. For the nitrogen monoxide, I used experiment 3 and experiment 4 because the hydrogen was held constant. And you should have gotten an order for the nitrogen monoxide of 2. So the rate law is rate is equal to the rate constant, don't forget the rate constant, times hydrogen times nitrogen monoxide squared. And the overall order is equal to 3. Because you have 2 nitrogen monoxides reacting with 1 hydrogen in order to make this reaction, let me rephrase, 2 nitrogen monoxides reacting with 1 hydrogen is the portion of the experiment that determines the rate of the reaction.
In the original, like, reaction, the coefficients don't mean anything.
For a rate law, the coefficients do not mean anything. The only way to determine your orders is through experimentation. So you can get experimental data to work from. Questions? In the lab, like I said, we will actually do this. We'll do an experiment where you have to use the method of initial rates. You'll be using the method of initial rates to determine the bleach, the order of the bleach. Now, as we're talking this thing, when we do the lab, which will be in a couple of weeks, you will be doing the method of initial rates to determine the order with respect to the bleach. And then we will use the integrated rate law, which we'll talk about on Monday, to determine the order with respect to the blue dye. So you're going to be using this to actually, these concepts in lab. Any questions before we depart? Don't forget, everybody in here, I think, is on the group meet for the class. So if you're having questions while studying, while I may or may not be awake to answer them, your classmates may. So don't forget to ask questions if you have the questions. That's why that whole class group was built. Is so that when there's problems, things can be answered. I will see you on Friday if I don't see you before. I will be there. I have an appointment at 9. It's like I will be there at 8:30. That's about all I have tomorrow.
Did work fine. Did work for my physics lab, and I was like, oh, it's a lot better.
I had something like that.
I just entered in this is the right page. These numbers right here,